Welcome to AI Agents and the Model Context Protocol. In this series, we're going on a deep dive into the architecture of sophisticated AI agent systems, from the low-level protocols that let them interact with the world to the high-level standards that will allow them to work together.
We want to move beyond the surface-level hype and get into the technical weeds. Our goal across these 9 episodes is to give developers, architects, and product leaders a comprehensive mental model for building, deploying, and governing agentic AI. We'll cover everything from agent architectures and memory to observability, safety, and much more.
Exactly. And the most fundamental question we can ask is, how does a large language model, which is essentially a text generation engine, actually do anything? How does it move from just predicting the next word to interacting with databases, APIs, and external systems? That bridge between reasoning and action is where our journey begins.
That's the perfect place to start. Today, we're exploring the foundational layer of that bridge, tool integration. We'll first unpack a new open standard called the Model Context Protocol, or MCP, that aims to universalize how agents connect to tools. Then we'll ground that theory in the practical reality of function and tool calling that developers are using today with models from providers like OpenAI and Anthropic. And finally, we'll discuss the critical, real-world challenges of making those connections reliable and secure.
So we're starting with the what and the how. What is this universal language for tools, and how do we implement it securely and robustly today? This is the bedrock upon which all other agent capabilities are built.
I think a great analogy for the Model Context Protocol is to think of it as the USB-C port for AI. Before USB-C, we had a chaotic mess of proprietary chargers and connectors for every device. You needed a different cable for your phone, your camera, your laptop. It was a nightmare of incompatibility. That's the state of AI tool integration right now. Many custom, brittle connectors that are hard to maintain.
So developers are building these one-off integrations for every tool and every model, what Anthropic calls the N by M data integration problem. For N models to connect to M tools, you need to build N times M custom connectors. It's inefficient and doesn't scale.
Precisely. MCP, which is an open standard introduced by Anthropic and built on the JSON RPC 2.0 protocol, aims to replace that mess with a single universal standard. It defines a clear, auditable way for an LLM, which it calls the host, to communicate with an agent, the client, and a tool provider, the server. Much like how the language server protocol standardized how IDEs could support different programming languages, MCP standardizes how AI applications can integrate with different tools and data sources.
And a key feature here is discovery, or introspection. The protocol allows the agent to ask the tool server what capabilities it has. It can call methods like list tools to see what's available, and get schema to understand the inputs and outputs for each tool. This means the agent can dynamically discover and use tools without them being hard-coded.
Exactly. Imagine a code review agent. Instead of having fragile prompt instructions telling it how to format a comment for a GitHub API, it can use MCP to discover the available tools from a GitHub server, see the required schema for creating a pull request comment, and then construct a valid JSON RPC call to execute it. It's a much more robust and structured interaction.
This sounds powerful as a future standard, but let's connect it to what developers are implementing right now. The core concept of an LLM generating a structured JSON object to call a function is already a reality with what's commonly known as function calling, or more recently, tool calling.
That's right. Major models from providers like OpenAI and Anthropic have this capability built in. While the underlying idea is the same, the implementation details vary slightly. For instance, with OpenAI's models like GPT-4o, you provide a list of available functions in a parameter named tools. Anthropic's Claude 3.5 Sonnet, on the other hand, uses a parameter called tool use to signal when it wants to invoke a tool.
And it's important for developers to stay current here. The older functions and function call parameters in OpenAI's API have been deprecated since late 2023 in favor of the more flexible tools parameter, which can support parallel function calls.
This is where theory meets reality. The model doesn't actually execute the code. It's a common misconception. The LLM's job is to act as a reasoning engine that, based on the user's prompt and the descriptions of the tools you've provided, decides which tool to use and generates the precise JSON object with the necessary arguments for that tool. Your application code then takes that JSON, executes the actual function, whether it's calling an internal API, querying a database, or anything else, and then sends the result back to the model to inform its final response.
So the developer is still in complete control. The LLM is just structuring the request. But this process introduces new points of failure. What happens if the model hallucinates an argument that doesn't fit the function schema? Or what if the external tool is temporarily down?
Now we're getting into the crucial topic of reliability. You absolutely cannot trust the model to always generate perfect, valid arguments. This is why external schema enforcement is non-negotiable. If your tool is a Python function, you can use a library like Pydantic to validate the incoming JSON from the model. If it doesn't match the schema, you don't even attempt to run the tool. You send an error message back to the LLM so it can correct itself.
That handles invalid inputs. What about external failures, like a network timeout or a 503 error from the API the tool is calling?
For those transient errors, you need a robust retry mechanism. A simple approach is to retry the call a few times, but a much better practice is to use exponential backoff, where you wait progressively longer between each retry. This prevents you from hammering a service that's already overloaded. For operations that must not be executed more than once, like processing a payment, the tool's API needs to be designed with idempotency. This is often done by passing a unique key with each request, so if the server sees the same key twice, it doesn't reprocess the payment and just returns the original result.
This is critical. Without idempotency, a simple network glitch during a retry could lead to a customer being charged twice. This brings us to an even bigger concern: security and governance. If we're giving an AI agent the ability to call tools that interact with real systems, how do we prevent it from doing something destructive?
This is arguably the most important piece of the puzzle. The foundational principle must be least privilege access. The agent should only have the absolute minimum permissions required to perform its task. Think of it like giving a valet a key that can only start the car and lock the doors. It shouldn't be able to open the trunk or the glove compartment.
In technical terms, this means using well-defined access control models, like role-based access control, RBAC, or attribute-based access control, ABAC, on the tools and APIs the agent can access. So an agent whose job is to read customer support tickets should never have write access to the production database.
Exactly. And every single tool call must be authenticated and authorized. It's also vital to run unsafe tool calls, like those that execute generated code, in a sandboxed environment to contain any potential damage. Beyond that, comprehensive and immutable audit logging is essential. You need to log every tool call with details on who or what initiated it, the exact parameters used, and the result. Without a clear audit trail, investigating incidents or ensuring compliance becomes impossible.
So to tie this all together, for agents to become powerful and autonomous, they need a standardized way to talk to the world, which is the promise of protocols like MCP. But in practice, today, this means carefully implementing tool calling with modern LLMs.
And that implementation has to be built on a foundation of resilience and security. That means validating every input, implementing smart retries and idempotency for reliability, and enforcing strict least privilege access controls with comprehensive auditing for security. Getting this right is what separates a clever demo from a production-ready, trustworthy AI agent.
We've established how an agent can securely and reliably interact with a single tool. But agents rarely perform just one action. They need to reason, act, and then reason again, sometimes chaining multiple tool calls together to accomplish a complex task. This requires a higher level of organization.
And that brings us perfectly to our next episode. Now that we have the building blocks of tool integration, we can begin to assemble them into more complex structures. We'll explore the different agent architectures and patterns, from simple React loops that interleave thought and action to more sophisticated planner-executor models, and even multi-agent systems where different agents collaborate to achieve a goal. We'll be moving up the stack from the protocol layer to the architectural layer.
Welcome to AI Agents and the Model Context Protocol. In our last episode, we established the foundational layer for AI agents, a standardized way for them to interact with the world through tools. But that raises a fascinating and much more complex question. Once an AI can use a tool, how do we design the AI itself to reason, to plan, and to tackle problems that require more than just a single action? How do we move from a simple tool user to an autonomous problem solver?
Exactly. It's like we've given our AI a universal toolkit, but now we need to provide the blueprint for the artisan. Today, we're exploring those blueprints, the agent architectures and patterns that give structure to an agent's thoughts and actions. We'll start by comparing the simplest form, a single agent system, to a more complex but powerful multi-agent approach. Then we'll dive into the cognitive loop at the heart of many agents, the react pattern. From there, we'll look at specialized patterns that grant agents capabilities like memory and self-correction, and finally, we'll discuss how to manage these complex systems using orchestration flows. These aren't just abstract designs, they are the core choices that determine whether an agent is efficient and reliable or chaotic and unpredictable.
An excellent roadmap. Let's start with that fundamental choice. Do we build one master agent or a team of specialists? What are the trade-offs between a single agent versus a multi-agent system?
This is one of the most critical decisions in agent design, and the best way to think about it is by comparing a solo craftsman to an entire assembly line. A single agent system, where one AI handles an entire workflow from start to finish, is like a craftsman building a custom piece of furniture. It's perfect for simple, linear tasks. For example, an agent designed to automate dependency updates in a codebase can follow a clear sequential process. Scan for outdated packages, check for compatibility, open a pull request, and report the status. It's efficient, easy to build, and straightforward to debug because there's only one actor.
So, simplicity and speed for well-defined isolated tasks. But I imagine that approach breaks down as the complexity of the task increases. You wouldn't ask one person to build a modern car from scratch.
Precisely. That's where multi-agent systems come in. For complex processes, it's far more effective to have a team of specialized agents, each an expert in its domain. Think about a sophisticated CRM system. Instead of one monolithic AI trying to do everything, you could have a lead scoring agent that analyzes new prospects, an email outreach agent that drafts personalized messages, and a follow-up agent that schedules reminders and tracks responses. Each agent has a single responsibility, which allows for parallelization. They can all be working at once, and incredible scalability. If your email outreach needs to grow, you can scale just that component without touching the others.
And that modularity likely makes the system more resilient. If one specialized agent fails, it doesn't necessarily bring down the entire operation. You can isolate and fix the issue within that single component. It introduces new challenges, though, like coordination and communication between the agents.
It absolutely does, and that's a perfect segue into our next topic. Whether you have one agent or a dozen, they all need a core logic loop to guide their behavior. This brings us to one of the most influential patterns in agent design, react.
React, which stands for reasoning and acting. It connects back directly to our last episode on tool calling because it's not just about the ability to act, but the cognitive process that decides which action to take and why.
Yes, React creates a dynamic feedback loop that mimics human problem solving. An agent operates in a continuous cycle of thought, action, and observation. Imagine a detective at a crime scene. First, there's the internal monologue, the thought. The witness's alibi seems shaky. I should verify their credit card transactions for the time of the incident. That's the reasoning part. The action is querying the financial database, a tool call. The observation is the result, a transaction record showing the witness was miles away. This new piece of information feeds back into the loop, triggering the next thought. Perhaps the alibi is false. Now I need to find evidence placing them at the scene.
So it's an iterative process of refining understanding and strategy based on real-time feedback from the environment or its tools. This sounds incredibly flexible, allowing the agent to adapt to unexpected information. But I've also read that this flexibility can be a double-edged sword. An agent in a react loop can sometimes wander aimlessly or get stuck in repetitive cycles if its reasoning isn't well guided.
That's the primary drawback. To counter that, there's an alternative model, the planner-executor pattern. If React is an improvising detective, the planner-executor is a meticulous engineer who refuses to start building until they have a perfect step-by-step blueprint. The planner, typically a powerful LLM, analyzes the overall goal and generates a complete multi-step plan up front. Then, the executor, which might be a simpler model or a set of specific functions, carries out each step of that plan sequentially.
This sounds far more deterministic and predictable. By forcing the agent to think through the entire process first, you get better performance and a lower chance of errors. The trade-off, I assume, is rigidity. What happens if an early step in the plan fails or the environment changes unexpectedly? The rest of the blueprint might become completely invalid.
Exactly. The planner-executor model struggles with dynamic environments where adaptation is key. In practice, many advanced systems use a hybrid approach, but these core patterns are often enhanced with other specialized capabilities.
Which brings us to patterns like memory, planning, and reflection. These seem less about the core cognitive loop and more about adding sophisticated layers of capability on top of it. Let's start with memory.
Memory-augmented agents are a huge leap forward because they introduce the concept of continuity. A stateless agent is like having a conversation with someone who has severe short-term memory loss. You have to re-establish context with every single turn. A memory-augmented agent, on the other hand, maintains a persistent state. It remembers previous interactions, user preferences, and the results of past actions. This memory can be a summarized conversation history or a structured user profile that is fed back into the model's context with each new request. It allows the agent to behave less like a stateless tool and more like an adaptive, personalized assistant.
And that persistence of knowledge is crucial for learning and improvement. That leads naturally to the idea of a reflection or feedback agent. It's not enough to just remember what happened, the agent needs to be able to learn from it.
This is where agents start to feel truly intelligent. A reflection agent incorporates a feedback loop to evaluate its own performance after a task is complete. Think of a professional sports team reviewing game footage. The game itself is the execution. The review session afterward is the reflection. They analyze what went well, what went wrong, and how they can adjust their strategy for the next opponent. An AI trading agent might do the same. After a series of trades, it could analyze the outcomes against its initial predictions and use that feedback to fine-tune its trading model. This process of self-critique and iterative refinement is what allows an agent to improve over time without constant human intervention.
So we have these powerful, specialized agents, potentially working in teams, equipped with memory and the ability to reflect. The final piece of the puzzle is managing the chaos. How do we make them all work together in a coordinated fashion? This is the challenge of orchestration.
Orchestration is about defining the traffic rules for your agents. For complex workflows, especially in multi-agent systems, you need a formal structure to manage the flow of tasks and information. One common approach is using directed acyclic graphs, or DAGs. Think of a complex recipe. You have to mix the dry ingredients before you add the wet ingredients, and you have to bake the cake before you frost it. A DAG represents this workflow as a series of nodes, tasks, and directed edges, ensuring that steps are executed in the correct order without any loops. Tools like Airflow and Prefect are often used to manage these kinds of data and AI pipelines.
That's a very structured, top-down approach. What about more dynamic scenarios where you don't know the full plan in advance?
For those cases, an event-driven architecture is often a better fit. Instead of a central controller assigning tasks, agents operate more autonomously, reacting to events that occur within the system. Imagine a series of dominoes. When one agent finishes its task, say our lead scoring agent identifies a high-value prospect, it emits an event. This event is broadcast to the system, and the next agent in the chain, our email outreach agent, is designed to listen for that specific event and is automatically triggered into action. This creates a loosely coupled system that is incredibly flexible and scalable.
And within multi-agent systems, there's also the idea of hierarchical control. This feels like the most intuitive model, as it mirrors a human organization.
It does. In a hierarchical system, you have a top-level supervisor or manager agent that receives a complex goal. Its job isn't to execute the task itself, but to decompose it into smaller subtasks and delegate them to the appropriate specialized subagents. For example, a travel planning request could be broken down by a manager agent and routed to a flight booker agent, a hotel agent, and an itinerary agent. The manager then aggregates the results to deliver the final, comprehensive travel plan. This architecture allows for both specialization and centralized coordination.
So, to summarize, the architectural choices we make are profound. We can choose between a simple, monolithic single agent or a scalable, specialized multi-agent system. At the core, an agent's behavior is driven by a cognitive loop, whether it's the flexible, iterative React pattern or the predictable planner-executor model. We can then layer on crucial capabilities like memory for continuity and reflection for self-improvement. And finally, we orchestrate these complex systems using structured flows like DAGs, dynamic event-driven architectures, or familiar hierarchical models.
Exactly. We've essentially designed the brain and the nervous system of our agent. But no matter how sophisticated that internal architecture is, its ultimate effectiveness is constrained by one thing: the quality of the information it can access. An agent with a brilliant reasoning engine is useless if it's working from a flawed or incomplete understanding of the world.
That is the perfect launchpad for our next episode. Having built the agent's mind, we now need to connect it to a world of knowledge. We'll be diving deep into the world of context management and retrieval, exploring how frameworks like retrieval augmented generation, or RAG, provide agents with access to external knowledge bases. We'll dissect the differences between vector and keyword search, discuss techniques for chunking and filtering information, and explore how to structure that information to minimize hallucinations and maximize relevance. Join us next time on AI Agents and the Model Context Protocol. You are listening to AI Agents and the Model Context Protocol. In our last discussion, we explored the fascinating world of agent architectures, from single and multi-agent systems to the intricate dance of reason and action in patterns like React. We saw how agents can be designed to plan, reflect, and collaborate. But a brilliant architecture is only half the story. An agent, no matter how sophisticated its design, is fundamentally limited by what it knows. This brings us to a critical question. How do we give our agents access to the vast, dynamic world of information that exists outside their pre-trained knowledge? How do we ensure their responses are not just plausible, but grounded in verifiable fact?
That's the core challenge we're tackling today. We're moving from the how of agent structure to the what of agent knowledge. It's about building agents that can learn and reason about information they've never seen before. Today, we'll be diving deep into the essential techniques for context management and retrieval. We'll start with the foundational framework of retrieval augmented generation, or RAG. Then, we'll dissect the two primary ways agents find information, vector and keyword search, and why the real power lies in combining them. From there, we'll get into the practicalities of preparing your data through chunking and filtering. Finally, we'll explore how to present this retrieved context to the model using structured inputs and outputs to ensure the agent's responses are not only accurate, but also trustworthy.
Exactly. These aren't just isolated techniques, they are the bedrock upon which reliable and truly intelligent agents are built. Without effective context retrieval, even the most advanced agent architecture is essentially operating in a closed room, only able to work with the information it was born with. By mastering these concepts, we open the door to that room, connecting our agents to live, authoritative data sources.
Think of it as the difference between a student taking a closed book exam versus an open book one. In the closed book scenario, the student, our LLM, can only rely on what they've memorized during their training. They might have a vast general knowledge, but they'll struggle with specifics, recent events, or proprietary information. The open book exam, however, changes the game entirely.
So the agent gets a textbook and an index.
Precisely. Retrieval augmented generation, or RAG, is the framework that facilitates this open book exam. At its heart, RAG is a two-step process. First, when a query comes in, the system doesn't immediately go to the LLM. Instead, it goes to a retrieval system, the index to our textbook. This system searches an external authoritative knowledge base, which could be anything from a company's internal documentation and product manuals to a vast collection of financial reports or legal documents. The goal is to find snippets of information or context that are highly relevant to the user's query. Only then, in the second step, is this retrieved context packaged along with the original query and sent to the LLM. The prompt essentially becomes, given this specific context, answer this specific question.
And this fundamentally changes the LLM's task. It's no longer just a knowledge recall problem, it's a reading comprehension and synthesis problem. This is critical for reducing the risk of hallucinations, where the model confidently states incorrect information because it's trying to fill gaps in its own knowledge. With RAG, we're providing the facts and asking the model to reason based on them.
Exactly. The quality of that retrieved context is therefore paramount. Garbage in, garbage out. This is where the mechanics of the retrieval system becomes so important. The most common approach involves creating what's called a vector database. We take our source documents, break them down into manageable pieces, and use a special type of model to convert each piece into a numerical representation, a vector. These vectors capture the semantic meaning of the text. When a user asks a question, their query is also converted into a vector, and the system finds the text chunks whose vectors are closest, mathematically speaking, in that high-dimensional space. This is semantic search. It's brilliant at understanding intent, synonyms, and paraphrasing.
So, if I search for quarterly revenue, a semantic search would also understand to pull up documents that talk about Q3 earnings, financial performance, or income statements, because the concepts are related, even if the exact keywords are missing.
Correct. But semantic search isn't a silver bullet. What if you need to find an exact term, a specific product SKU, a legal clause, or a particular person's name? Semantic search can sometimes generalize too much and miss these precise, literal matches. That's where the older, more traditional, keyword search, often using algorithms like BM25, still reigns supreme. It excels at finding exact textual matches. If you search for net income, it will find every instance of net income.
It sounds like you're setting up a scenario where you really need both, one for understanding conceptual similarity and the other for pinpoint precision.
That's the key insight that leads to the most robust retrieval systems, hybrid search. The best practice is to run both a semantic search and a keyword search in parallel for the same query. You get a set of results from the vector search and another set from the keyword search. Then you merge these results, often using a process to deduplicate and re-rank them to get the final context that's passed to the LLM. This dual approach maximizes recall, ensuring you don't miss relevant information, whether it's conceptually related or a literal match.
I can see how that would be powerful. Let's take the example of a financial co-pilot analyzing company reports. If an analyst asks, what was the sentiment around our Q3 earnings and what was the exact net income figure, a hybrid system is essential. The semantic search would pull in analyst commentary and executive summaries that discuss the feeling and context of the earnings call, while the keyword search would simultaneously pinpoint the exact line item in the 10Q filing that states the precise net income figure. Relying on only one method would likely give you an incomplete answer.
And that brings us to the next practical challenge. How do we prepare those documents for searching in the first place? You can't just feed an entire 100-page PDF into a vectorizer. The context would be too broad and noisy. This is where the art of chunking comes in. The goal is to split long documents into smaller, self-contained chunks of text. You want each chunk to be semantically meaningful on its own. For example, you might split a document by paragraphs or sections.
But if you just split it cleanly at the end of every paragraph, you might sever a thought that carries over into the next one.
An excellent point. That's why a common and effective strategy is to use overlapping chunks. When you create your chunks, you include a small amount of text from the end of the previous chunk at the beginning of the next one. This creates continuity and ensures that a concept isn't awkwardly split right at a boundary, which could cause it to be missed during retrieval. Once you have these well-defined chunks, they can be scored for relevance using metrics like cosine similarity, which measures the angle between the query vector and the chunk vector.
So you get a ranked list of the most relevant chunks. But is that always enough? What if the top results are all from an outdated document or from a completely irrelevant department's knowledge base?
That's where filtering and re-ranking add another layer of precision. Each chunk shouldn't just be a blob of text. It should have metadata associated with it, things like the document's creation date, its source, its author, or domain tags. This allows you to apply filters either before or after the initial search. You could, for instance, tell the system to only retrieve chunks created in the last year, or only from documents tagged as official HR policy. For even higher precision, especially when the top few results are very similar, you can use a more computationally expensive but powerful technique, an LLM cross-encoder. Instead of just comparing the query vector to the chunk vector, a cross-encoder looks at the query and a potential chunk together and outputs a more accurate relevance score. This helps you re-rank your top hits to ensure the absolute best context goes to the main LLM.
We've successfully retrieved a set of highly relevant, filtered, and ranked chunks of information. Now we have to actually hand it over to the language model. How we do that seems just as important as the retrieval itself.
It's absolutely critical. You can't just dump the text into the prompt and hope for the best. The model needs clear instructions on how to use the information. Best practice is to use a structured prompt format. You create a designated section, often explicitly labeled like context, followed by the concatenated document excerpts. Then you place your question, such as, using only the context provided, answer the following question. This formatting helps the model understand the hierarchy of information, that the provided context is the ground truth for this specific task.
And this is where we can really start to exert control over the output and mitigate hallucinations.
Yes, we can go a step further and enforce a structured output using JSON or YAML schemas. For example, you could instruct the model to always respond with a JSON object that contains two fields, answer and source. In the prompt, you would provide instructions and an example of this format. This forces the model to not only generate the answer, but also to identify which part of the provided context it used to formulate that answer.
So you're compelling the model to cite its sources. This seems like a powerful mechanism for building trust. A support agent, for instance, could provide an answer and then add a footnote like, this information is based on page 5 of the User Installation Guide, published in October 2025. The user can then verify the information themselves if they wish.
And it also gives us a lever for when the model can't find the answer. Part of the instruction in the prompt should be a fallback rule, something like, if the answer cannot be found in the provided context, output, I could not find a reliable source for this information. This prevents the model from guessing or inventing an answer when the retrieved context is insufficient. It's about teaching the agent intellectual honesty.
That makes sense. But what about scenarios where the retrieval process pulls up a very large amount of relevant context, say dozens of documents? We can't always fit all of that into the model's limited context window.
That's a common challenge, and it requires a strategy for summarization or compression. Before passing the context to the main reasoning LLM, you can use another, often smaller and faster LLM to perform a pre-processing step. This model can take a set of similar documents and condense them into a single, concise summary that captures the key points. Alternatively, you could prune the context by relevance scores, only keeping the absolute top-ranked chunks. This is also closely related to how agents manage memory over a long conversation. Older parts of the dialogue can be summarized into a brief memory to save space while retaining the essential context.
So effective context management is a multi-stage pipeline, starting with hybrid search for broad recall, then intelligent chunking and filtering for precision, and finally, structured prompting and summarization to ensure the LLM can use the information reliably and efficiently. It's a system designed to ground our agents in reality.
That is the key takeaway. Building a powerful AI agent isn't just about picking a great model. It's about building the infrastructure around it that feeds it the right information at the right time in the right format. RAG, hybrid search, and structured data handling are the tools that transform an LLM from a creative but sometimes unreliable conversationalist into a knowledgeable and trustworthy expert assistant. It's the difference between an agent that might know the answer and one that knows how to find it.
And knowing how to find information is just the beginning. Once an agent has this context, how does it remember it across conversations? How does it build a persistent understanding of a user or a task over time? That's where the concept of memory comes in, and it's a fascinating and complex topic.
It certainly is. We've touched on summarization as a way to manage context, but that's really just scratching the surface of agent memory. In our next episode, we'll dive deep into the distinction between short-term and long-term memory for agents, exploring how they store and recall information, from specific past events to general knowledge, and the critical importance of privacy and the right to be forgotten in these systems.
You're listening to AI Agents and the Model Context Protocol, where we explore the architecture of intelligent systems.
Today, we're moving beyond the immediate and into the persistent. We're asking a question that separates a simple tool from a true collaborator. How does an AI agent remember?
In our last discussion, we broke down the mechanics of context retrieval, how an agent can pull in external knowledge using techniques like RAG to answer a question accurately in the moment. But that's only half the story. What happens when the user comes back tomorrow or next week? How does the agent recall their preferences, learn from past failures, and build a continuous, evolving understanding?
This is the entire discipline of memory in AI agents. It's the mechanism that enables statefulness and learning over time. Today, we'll be dissecting the core distinction between an agent's short-term and long-term memory.
We'll also go a level deeper, exploring the difference between remembering specific events, which is known as episodic memory, and recalling general facts, or semantic memory.
And critically, we'll ground this in engineering reality. We'll discuss the databases and caches used as memory stores, the policies required to keep that memory relevant and accurate, and the unavoidable ethical guardrails of privacy and a user's right to be forgotten.
So let's begin with that foundational split. When we talk about short-term versus long-term memory for an agent, what are we really describing from a systems perspective?
It's a conceptual model that maps very closely to the practical implementation. Short-term memory, or STM, is the agent's working scratchpad. It's the context for the current task. This includes the last few turns of a conversation, the parameters for a tool it's about to use, or the steps in a multi-part plan it's executing. From a technical standpoint, this is often held directly within the LLM's context window or in a fast external key-value store like Redis.
Meaning it's highly accessible but also fundamentally ephemeral. It has a limited size, the context window can only hold so many tokens, and if the session ends or the conversation gets too long, that information is lost unless it's explicitly preserved. It's the agent's active RAM.
Precisely. And the act of preserving it is what transitions information to long-term memory, or LTM. This is the agent's persistent, durable knowledge store. It's where the agent archives information that needs to survive across sessions. This isn't just a raw log, it's structured knowledge. It could be a user profile that tracks preferences, a database of summarized past interactions, or a set of learned facts about the world.
This is where the retrieval systems we covered last time become so critical. The LTM is the vast library of everything the agent knows, but to be useful, it needs an efficient librarian. So the LTM might be a vector database of conversation summaries, and when a user starts a new chat, the agent performs a similarity search to retrieve the summary of their last interaction, loading it into its short-term memory to pick up where they left off.
That's the exact workflow. LTM provides the persistent knowledge, retrieval surfaces the relevant pieces, and STM holds that surfaced knowledge for immediate use. Think of a seasoned financial analyst. Their short-term memory is the clutter of stock tickers, news alerts, and calculations on their screen for the analysis they're doing right now. It's vital, but it's for the current task.
It's the immediate data fueling the immediate decision.
Exactly. Their long-term memory, however, is the cumulative knowledge they've built over a decade. It's the deep understanding of market cycles, the history of a specific company's performance, the nuances of its leadership. They don't keep all of that on their screen at once. When a new earnings report comes out, a new prompt in our world, they use that cue to retrieve long-term knowledge, pull it into their active thoughts, and synthesize it with the new, short-term data to form a conclusion. That synthesis is what an advanced agent strives for.
And this leads to a more subtle but equally important distinction within that long-term memory. It's not just a single monolithic block of information. We need to differentiate between what the agent knows and what it has experienced. This is the split between semantic and episodic memory.
A critical distinction for building agents that don't just recite facts, but actually learn from their actions. Semantic memory is the agent's textbook knowledge. It's a collection of general, context-free facts. For a customer service agent for an electronics company, its semantic memory is the vectorized product manuals, the specification sheets, the official troubleshooting guides. It knows that Model Z has a 4,000 milliamp hour battery, and to reset Model Z, hold the power button for 10 seconds.
It's the objective source of truth, the encyclopedia.
Correct. Episodic memory, by contrast, is its personal diary. It records the context-specific events the agent has personally experienced. It's the memory of specific interactions. An entry might look like, on Monday, I walked a user through the official reset process for Model Z, and it didn't solve their battery drain issue. The user later discovered a third-party app was the cause. This is not a fact from the manual. It's a lived experience.
So the next time a user complains about battery drain on a Model Z, the agent can do something much more intelligent than just reciting the manual. It can consult its semantic memory for the official process, but also its episodic memory for past case outcomes.
And that's the key. It can now reason based on precedent. It might say, we can start with the official reset process. However, I've seen cases where third-party applications can cause this kind of battery drain. Have you installed any new apps recently? That is a huge leap in capability. It moves from basic retrieval to case-based reasoning, learning from its own operational history.
This sounds incredibly powerful, but also computationally and logistically complex. Storing every single interaction forever is not feasible. This brings us to the practicalities. How do you build and, more importantly, maintain these memory systems without them becoming bloated, outdated, and useless?
This is the core engineering challenge, and it's solved with a combination of the right data stores and intelligent management policies. For stores, as we've hinted, it's rarely one-size-fits-all. LTM is often a hybrid, a relational database like PostgreSQL for structured user data, paired with a vector database like Pinecone or Chroma for storing and searching on the semantic meaning of unstructured text like conversation summaries. STM is usually a much faster, simpler cache.
But the real complexity lies in the policies. You can't just write to these databases indefinitely.
Absolutely not. You need active memory management, the first pillar of which is a decay or refresh policy. Information, like organic memory, has a half-life. A user's specific complaint from 2 years ago is likely less relevant than one from last week. A decay policy might automatically downrank the retrieval score of older memories. A pruning policy might be more aggressive, summarizing conversations into a single vector after 90 days and deleting the raw logs entirely after a year to comply with data retention rules.
This also guards against the agent acting on stale information, which brings up the idea of grounding memory.
Memory grounding is the second pillar, and it's about ensuring the LTM reflects the current source of truth. An agent's memory can't be an island. If an agent remembers a user's shipping address, that's useful. But if the user updates their address in their main account profile, the agent's memory is now dangerously out of date. A grounding policy would dictate that the agent must periodically revalidate that piece of memory against the central CRM database, ensuring it doesn't confidently ship a package to the wrong state.
So it's a constant process of curation. The agent's memory isn't a stone tablet. It's more like a living document.
A perfect way to put it. I often use the analogy of a digital gardener. The agent's long-term memory is its garden. Simply throwing new seeds in constantly will result in a chaotic, overgrown mess. Pruning is your decay policy. You trim back the old, woody branches that no longer provide value. Grounding is like testing the soil. You're checking your foundational facts against a source of truth and amending them as needed. And summarization is like composting. You're taking bulky raw material, the verbose transcripts of old conversations, and breaking them down into a dense, nutrient-rich format that's easier for the agent to absorb and use in the future.
This systematic management of memory, storing, pruning, and grounding inevitably leads us to the most sensitive part of this discussion: privacy. We are, by definition, creating a system that records user interactions.
And this is where engineering meets ethics and law. It is the most important constraint on any memory system you build. The first principle is data minimization. Do not store what you don't absolutely need. Does your support agent need to remember a user's name to be helpful? Probably. Does it need to remember their credit card number or social security number? Absolutely not. Any sensitive, personally identifiable information, PII, that must be stored needs to be handled with extreme care, ideally encrypted at rest and in transit.
This extends beyond just avoiding storing sensitive data. It's also about giving users control over their own data.
It is. Regulations like GDPR in Europe establish a user's right to be forgotten. This is a technical requirement. Your system architecture must be designed to handle a deletion request. When a user invokes this right, you need a reliable process to go through all of your memory stores: the SQL database with their profile, the vector store with their summarized interactions, the raw logs in your object store, and permanently delete all data associated with that user. It's not optional. It's a foundational requirement for building trustworthy AI.
So, to bring it all together, memory is what truly elevates an agent. It provides the continuity and context that allows for genuine learning and personalization, moving us from single-shot answers to an ongoing, stateful dialogue.
The key insight for anyone building these systems is that memory is not a passive data dump. It's an active, managed system. A successful implementation requires a thoughtful architecture that separates fleeting short-term context from persistent long-term knowledge, and further divides that knowledge into factual semantics and experiential episodes.
And this entire structure must be governed by rigorous policies. Policies for managing size and relevance through decay, for ensuring accuracy through grounding, and for upholding user trust through strict privacy controls and the right to be forgotten.
Exactly. And managing this dynamic interplay of memory stores, retrieval functions, and privacy policies introduces a new level of complexity. The agent needs an internal controller to decide when to access memory, what to store, and how to chain these actions together with tool use.
Which sets the stage perfectly for our next episode. Now that we've built an agent with the ability to use tools and the capacity to remember, we need to direct its behavior. We'll explore the critical layer of orchestration and observability, how we can use routers and state machines to manage complex agent workflows, and how we can implement logging, tracing, and metrics to ensure our increasingly autonomous agents are operating safely, efficiently, and as intended.
We'll be moving from the agent's mind to its central nervous system. It's going to be a fascinating discussion.
Welcome to AI Agents and the Model Context Protocol. In our last discussion, we explored the crucial role of memory, how agents recall past interactions and knowledge to inform their current actions. But once an agent has access to that memory and a set of tools, how does it decide what to do next? What happens when a task isn't a single action, but a complex, multi-step process?
That's the core question we're tackling today. We're moving from the agent's internal state, its memory, to its external actions and the systems that manage them. It's one thing to have a smart individual, but it's another entirely to coordinate a team of specialists to achieve a complex goal. This episode is about building that team and, just as importantly, watching over their work to make sure everything runs smoothly. We'll be diving into orchestration, which is how we manage complex agent workflows, and observability, the practice of monitoring and understanding what our agents are actually doing.
Exactly. We'll start with the traffic cops and rule enforcers of the agent world, routers and guardrails. Then we'll explore the sophisticated frameworks that act as project managers for our agents, known as workflow engines. After that, we'll shift our focus to observability, breaking down the vital practices of logging and tracing to get a clear picture of an agent's behavior.
And we'll get specific on what to measure, from core infrastructure metrics to the AI-specific signals that tell us if our agents are healthy, efficient, and effective. It's a journey from directing the flow of tasks to deeply understanding the performance at every step. This is the bridge from a single functional agent to a robust, production-ready system of agents.
Let's start at the decision point. A user sends a query. In a simple system, one agent handles it. But what if the query is, what are the legal implications of our new marketing copy for the European market? That's not one task, it's at least two.
And this is where the concept of a router comes into play. A router, in this context, is essentially a specialized agent whose primary job is to dispatch tasks. It's like a sophisticated receptionist in a large corporation. It doesn't answer the complex questions itself, but it knows exactly who to send you to. It analyzes the incoming query, legal implications, marketing copy, European market, and determines that this requires expertise from both the legal and the marketing departments. The router agent, often a fine-tuned LLM itself, would then route the query to a specialized legal sub-agent and a technical marketing sub-agent.
So it's a classification and delegation step. The router adds a layer of intelligence before the main task is even attempted, ensuring the right tool, or in this case, the right specialized agent, is engaged from the start. This prevents a general-purpose agent from struggling with a highly specific task it's not equipped for.
Precisely. And alongside this delegation, we need rules of engagement. This is where guardrails come in. Guardrails are policy engines that act as a continuous check on the agent's outputs. They aren't concerned with how the agent does the work, but with what it produces. These are the compliance officers of the AI world. For instance, a guardrail could enforce a rule that prohibits the generation of profane language. Another could prevent the agent from executing certain commands, like deleting a production database, even if a user cleverly tries to trick it into doing so.
So, the router decides who does the work, and the guardrails ensure the work is done within acceptable boundaries. It's a system of checks and balances. The router provides efficiency, and the guardrails provide safety and compliance.
Think of it like a self-driving car. The router is the navigation system, deciding whether to take the highway or local roads based on the destination and traffic. The guardrails are the safety systems, the automatic emergency braking, the lane keep assist, that constantly monitor the car's actions to prevent it from violating critical safety rules, regardless of the chosen route. You need both to operate effectively and safely.
This routing and guarding works well for single-step decisions. But what about that marketing campaign example? It's not just one decision, it's a sequence. First, generate the ad copy. Then, schedule the social media posts. And finally, after some time, analyze the performance data. This is a workflow with dependencies.
Exactly. And this is where simple routing isn't enough. We need a more structured approach, which brings us to workflow engines. These are frameworks designed to manage complex, multi-step agentic processes. They allow us to define the flow of work as a state machine, or, more commonly, a directed acyclic graph, a DAG. Each node in this graph can be an agent, a tool call, or a specific function.
So in our marketing campaign example, generate copy is the first node. The output of that node, the ad copy, becomes the input for the schedule posts node. And the success of that node triggers the analyze performance node down the line. The graph structure defines the dependencies and the order of operations.
It's like a highly automated, intelligent assembly line. But instead of car parts, we're moving data and tasks between specialized AI agents. Frameworks like LangGraph, CrewAI, and AutoGen are built specifically for this. They provide the scaffolding to build these reliable, repeatable workflows. LangGraph, for example, explicitly uses the state machine concept, where each agent's action modifies a shared state that is passed to the next agent in the graph. This ensures everyone is working off the same, most up-to-date information.
It's a way of composing agentic capabilities. Instead of building one monolithic agent that has to do everything, you build smaller, specialized agents and then use an orchestration engine to chain them together in sophisticated ways. This seems far more scalable and maintainable.
Infinitely more. Imagine a professional kitchen preparing for a dinner service. You don't have one chef doing everything. You have a head chef who is the orchestrator. They don't chop the vegetables or sear the steak. They have a prep chef, a grill chef, and a pastry chef for that. The head chef's role is to define the workflow. Prep chef, I need the mirepoix ready in 10 minutes. Once that's done, grill chef, you'll get it to start the sauce base while you're also searing the steaks. The orchestration engine is the head chef, the specialized agents are the line cooks, and the DAG is the recipe they're all following. This system ensures reliability and quality at scale.
That's a perfect analogy. And just like in a real kitchen, if something goes wrong, if the sauce burns or a steak is overcooked, the head chef needs to know immediately. They need visibility into the entire process. This brings us directly to the other side of the coin, observability.
Yes, orchestration without observability is like flying blind. You can set up the most brilliant workflow, but if you can't see what's happening inside it, you can't fix it when it breaks, and you can't improve it. This is where we get into the nitty-gritty of logging and tracing. We need to collect detailed evidence of every step the agent takes.
And this is more than just a simple task completed log. For true observability, we need rich, structured data. We need a complete trace of the agent's journey. This includes a timestamp for every single LLM call, the exact input prompt that was sent, the raw output received from the model, and a detailed record of any tools that were used, including the parameters they were called with and the results they returned.
This collection of data is often referred to by the acronym MELT, Metrics, Events, Logs, and Traces. It provides end-to-end visibility. A trace ties all these pieces together into a single cohesive story of a single transaction. You can see the initial user query, the router's decision, the sub-agent's prompt, the tool call it made, the data it got back, its final response, and the guardrails check on that response. It's like having a black box flight recorder for your AI agent.
With that level of detail, debugging goes from guesswork to a data-driven process. But MELT also includes metrics. This is about aggregating the data from all those traces to see the bigger picture. What are the key metrics we should be monitoring for an agentic system?
The metrics fall into two broad categories. First, there are the standard infrastructure metrics you'd monitor for any software application: CPU and GPU load, memory usage, and network latency. These are foundational. If the server is down, the agent is down. But then we have the AI-specific signals, which are far more interesting. The most obvious one is token usage. Since most powerful models charge per token, this directly translates to cost. A sudden spike in token usage per query is an immediate red flag that needs investigation.
Right. That could indicate an agent getting stuck in a loop or generating unnecessarily verbose outputs. Response latency is another critical one. How long does it take from the user's query to the final answer? If that starts to creep up, user experience suffers.
And we also need to track metrics related to the model's behavior and the tools it uses. We should monitor model confidence scores if the model provides them, to watch for model drift, where the model's performance degrades over time on your specific tasks. Crucially, we have to count errors, specifically tool failures. How often are our agents trying to use a tool and failing? Is it because the agent is formatting the request incorrectly, or is the tool's API itself unreliable? Without logging this, you'd never know where the problem lies.
You also mentioned tracking response quality through sampling and feedback. This feels less automated.
It can be a mix. You can have automated checks for certain quality aspects, but human-in-the-loop feedback is invaluable. This could be as simple as a thumbs up/thumbs down button for users, or a more formal process where a sample of agent conversations is reviewed by human experts periodically. These quality scores become a critical long-term metric. The goal is to put all of this on dashboards. You want to be able to glance at a screen and see the health of your agent system: cost per query, average latency, tool error rate, and user satisfaction score. And you set up alerts for anomalies. If the token count per query suddenly doubles or the error rate jumps by 20%, an alert should fire, telling your team to investigate.
This sounds incredibly powerful, but also complex to build from scratch. Are there tools that specialize in this kind of AI observability?
Absolutely. Building this level of telemetry is a significant engineering effort, so a number of specialized platforms have emerged to handle it. Tools like LangSmith, LangFuse, and LangWatch are designed specifically for this. They provide SDKs that you can easily integrate into your agent's code to automatically capture all of this rich data. The prompt/response pairs, the tool calls, the latencies, the token counts. They provide the dashboards, the tracing UIs, and the analytics tools out of the box.
So you could use one of these tools to diagnose a real-world problem. Let's say we have an IT ticketing agent. Its job is to help employees with common IT issues. We deploy a new version, and a day later, we notice on our dashboard that the average time to resolve a ticket has spiked.
Perfect example. With a tool like Langfuse or Langsmith, you could dive right in. You'd filter the traces for the new agent version and look for patterns. You might compare the traces of slow tickets against the traces of fast tickets. In those traces, you might discover that the new version is consistently failing when it tries to call a specific tool, like the Reset Password API. It tries, fails, and then spends several extra turns apologizing to the user and asking them to try again manually, all of which increases the resolution time.
And the logs would show the exact error message from the API call, revealing that perhaps the new model is sending a parameter in the wrong format. Without that detailed trace, you would just know that things are slower, but you wouldn't know why. The observability platform would pinpoint the exact stage in the orchestrated workflow that's failing.
And that's the beautiful synergy between orchestration and observability. Your orchestrator defines the complex workflow, and your observability platform gives you the microscope to inspect every single step of that workflow. You can't have a reliable, scalable, and continuously improving system of agents without both. They are two sides of the same coin. Orchestration builds the machine, and observability gives you the control panel and the diagnostic readouts.
It's a powerful combination. We've defined how to direct agents with routers, constrain them with guardrails, and build complex multi-step processes with workflow engines. And we've established the critical need to watch over them with detailed logging, tracing, and metrics to ensure they are performing as expected.
This really sets the stage for the next logical question. Now that we can build and observe these complex agent systems, how do we know if they're actually any good? How do we measure success? It's one thing to know that the agent resolved a ticket. It's another to know if it did so correctly and efficiently.
Which leads us directly into our topic for the next episode, evaluation and benchmarking. We'll explore how to define success metrics, the difference between offline benchmarks and online evaluation, and how to build a feedback loop for continuous improvement. It's the process of moving from "is it working" to "how well is it working?" Welcome to AI Agents and the Model Context Protocol. In our last discussion, we navigated the intricate world of orchestration and observability, laying down the tracks and installing the sensors for our AI agents. We learned how to build complex workflows and, crucially, how to watch them operate. But seeing what an agent does is only half the story. The real question, the one that separates a clever prototype from a reliable system, is this: is it any good?
Exactly. It's one thing to build a complex, multi-agent system that can call tools and route queries. It's another thing entirely to prove that it's effective, accurate, and trustworthy. That's the chasm we're crossing today. We're moving from orchestration, which is the how, to evaluation, which is the how well. Today, we'll explore how to define and measure success. We'll dive into the world of offline benchmarks versus online real-world testing, and most importantly, we'll discuss how to close the loop and create a system of continuous improvement.
So, let's start at the most fundamental point. Before we can measure anything, we have to define what we're measuring against. What does success even mean for an AI agent? It seems deceptively simple, but the answer can be quite nuanced. We can't just rely on a gut feeling that the agent is working. We need concrete, quantifiable metrics.
That's the foundation of it all. You can break it down into a hierarchy of success. At the highest level, you have task and workflow success. Did the customer support agent actually resolve the user's ticket? Did the financial agent complete the quarterly report calculation correctly? This is the binary top-line outcome. But to understand why it succeeded or failed, you have to look deeper.
And that next layer down is the tool invocation level. An agent's overall task is composed of many smaller steps, many of which involve using a tool. The workflow might fail not because the LLM's reasoning was flawed, but because an API call failed, or the model formatted a request incorrectly, leading to a parsing error. Logging these specific error types, distinguishing between a network timeout and a malformed JSON output, for instance, is critical for debugging.
Think of it like a master chef overseeing a complex recipe. The final dish being delicious is the ultimate success metric. But if it fails, you need to know why. Was the oven temperature wrong? That's a tool failure. Did the sous chef misread the recipe? That's a reasoning error. Did they grab salt instead of sugar? That's a factual error. Which brings us to one of the biggest challenges in evaluation: factuality and its nemesis, hallucination.
This is especially critical in retrieval augmented generation, or RAG systems, where the agent is supposed to answer based on a specific set of documents. How do we ensure the agent is being faithful to the source material and not just making things up that sound plausible?
This is where a suite of RAG-specific evaluation metrics becomes indispensable. The first is faithfulness, which you can think of as a grounding check. We programmatically verify that the generated answer actually cites and is supported by the retrieved source context. If the agent says the report states X, we need to be able to trace X directly back to the provided document. Next is answer relevance. Does the answer actually address the user's specific question? The agent might give a factually correct statement from the source, but if it doesn't answer the query, it's failed.
And then there are the metrics that evaluate the retrieval part of the process itself.
Precisely. We have contextual precision, which asks, of all the documents the retriever pulled up, how many were actually relevant to the question? You don't want to feed the generator a lot of noise. And its counterpart is contextual recall, which asks, of all the relevant documents that exist in the knowledge base, how many did the retriever successfully find? You might have high precision but low recall, meaning you find good stuff but miss a lot, or vice versa. Evaluating these four metrics, faithfulness, relevance, precision, and recall, gives you a comprehensive picture of your RAG agent's performance, far beyond a simple, was the answer right?
This systematic approach feels robust, but it runs into a familiar challenge with LLMs: their inherent randomness. How can you reliably diagnose a problem if the agent gives you a slightly different bad answer every time you run the same test? This brings up the tension between determinism and stochasticity.
It's a classic balancing act. During evaluation and debugging, you want to eliminate as much randomness as possible. You'd set the model's temperature parameter to a very low value, close to 0. This makes the output deterministic. The model will almost always pick the most probable next token. If there's a flaw in your prompt or logic, you'll get the same flawed output consistently, making it much easier to identify and fix the root cause. You're essentially holding the variable steady to conduct a clean experiment.
But in a production environment, that deterministic, predictable response might feel robotic or stale. For creative tasks, like drafting marketing emails, you might actually want that diversity.
Exactly. In production, you might increase the temperature to encourage more varied and creative outputs. But you can't just set it and forget it. You have to monitor the variance in the outputs. If the responses become too erratic or start to drift off topic, you know your temperature is too high. It's a dial you tune based on the specific use case: low and steady for analytical tasks, higher and more dynamic for creative ones.
So once we have our metrics and we've controlled for randomness, we need a standardized way to test our agent's capabilities. We need a proving ground. This is where offline benchmarks come into play. These are like standardized academic tests for models and agents.
They're absolutely essential for comparing models and tracking progress over time. And the landscape of benchmarks is becoming increasingly specialized. For general coding tasks, you have things like SWE-bench. For tasks involving operating a computer, navigating file systems, and using applications, there's the OS World benchmark. These test suites provide a standardized set of problems to see how different agents stack up. For instance, we know that some of the latest models can achieve scores in the 60 to 80% range on these complex benchmarks, which gives us a concrete sense of the current state of the art.
And for the RAG systems we just discussed, there are now a whole host of specialized benchmarks as well, like CR-RAG, Legal Bench RAG for the legal domain, and T2 RAG Bench. These don't just test the model's knowledge, but its ability to perform the entire retrieve and synthesize process accurately.
And using these benchmarks is like running your agent through a gauntlet. But there's a critical pitfall to avoid: overfitting to the benchmark. A benchmark is a static snapshot. The real world is not. If you build a financial agent, you can't just test it on last year's regulatory filings. Your internal test suites must be living documents, continuously updated with new, real-world user scenarios. Otherwise, you're just teaching your agent to pass an old test, not to solve current problems.
This is the perfect transition from the lab to the real world. Offline benchmarks are crucial, but the ultimate test is how the agent performs with live traffic and unpredictable users. This is the domain of online evaluation.
This is where the rubber meets the road, and you don't want to just flip a switch and send 100% of your users to a new, untested agent version. That's a recipe for disaster. Instead, you use careful, controlled rollout strategies. A canary deployment is a great example. You can route a very small fraction of live traffic, say 1%, to the new version of your agent. The other 99% continue to use the stable old version.
This allows you to compare key metrics in a live head-to-head competition. You're not just looking at accuracy anymore, you're looking at business and user experience metrics. Is the new version using more tokens and driving up costs? Is its latency higher, making users wait? Are users abandoning the conversation more frequently? These real-time feedback loops are your early warning system.
It's like a restaurant testing a new recipe. They don't replace their most popular dish overnight. They offer the new dish as a special to a few tables. They watch carefully. Do people finish it? Do they order it again? Do they complain? The feedback from those first few customers determines if the dish makes it to the permanent menu. A/B testing is a more formal version of this, where you might route 50% of traffic to version A and 50% to version B to see which one performs better against a specific goal, like conversion rate or task completion.
So we've defined our metrics, we've tested in a controlled offline environment, and we've gathered data from a live online test. The final piece of the puzzle is turning all of that analysis into action. This is the continuous improvement loop.
This is what separates the great AI products from the mediocre ones. Evaluation isn't a final exam, it's a continuous learning process. When you find failures, and you will find failures, you have to perform a rigorous analysis. Was it a bad prompt, a limitation in the model's reasoning, a bug in a tool, or is your source data out of date? Each failure is a learning opportunity.
And this leads to establishing baselines. Once your agent is running, you should know its expected success rate. For example, your ticket resolution agent might successfully close 85% of cases on its own. You set that as your baseline. If that metric suddenly drops to 75%, it should automatically trigger an investigation. This brings us back to the observability we discussed in the last episode. Your metrics and dashboards are what make these deviations visible.
And the loop closes with automated retraining. The world changes, so your agent must too. This is the concept of data drift. The kinds of questions users ask today might be different from the ones they asked 6 months ago. You need automated pipelines that can take the new data, the failure cases you've identified, and use them to refine your system. This might mean fine-tuning the LLM itself on a new dataset, or it could be as simple as using the new data to generate better examples for your prompts in a process called prompt tuning.
It's a complete living ecosystem then. You define success, test against it offline, validate it online, and use the data from both to continuously refine and retrain the system, which in turn improves the metrics you started with.
That's the cycle. It's a flywheel. Each rotation, each evaluation cycle, makes the agent smarter, more reliable, and more effective. It transforms the agent from a static piece of code into a dynamic system that adapts and learns from its environment. And building a well-evaluated, continuously improving agent is the foundation for making it a trustworthy one.
It's clear that evaluation is not just a single step in the development process, but a continuous and essential discipline that underpins the entire life cycle of an AI agent. It's how we ensure these powerful systems are not just capable, but also consistently effective and reliable.
And now that we've established how to measure if our agent is good at its job, we have to tackle an even bigger question. How do we ensure it's safe and acting responsibly while doing it? That's where we're heading in our next episode, into the critical domain of safety, governance, and compliance, where we'll discuss everything from data privacy and access control to sandboxing and supply chain trust.
Welcome to AI Agents and the Model Context Protocol. In our last discussion, we navigated the critical landscape of evaluation and benchmarking, establishing the metrics and methods to answer the question, is our agent effective? We learned how to measure success, how to benchmark performance, and how to create a cycle of continuous improvement. But an agent that is powerful and effective is only half the story. An equally, if not more important question is our agent safe?
Exactly. Building a high-performing agent without guardrails is like engineering a sports car with a powerful engine but no brakes and no seatbelts. It might perform brilliantly on a closed track, but it's a disaster waiting to happen on a public road. Today, we're installing those safety features. We're moving from performance to protection, exploring the essential trinity of safety, governance, and compliance. We'll be dissecting how to manage the data our agents consume, how to contain their actions in secure environments, and how to build a chain of trust from the foundational model all the way to the final output.
These aren't just checkboxes on a compliance form. They are the bedrock of building trustworthy AI. Without them, even the most capable agent becomes a liability. Let's start with the fuel that powers these agents, data. The sheer volume and sensitivity of information an agent might have access to presents an enormous governance challenge.
It really is the first line of defense. The core principle here is data minimization, which is a concept security professionals have been championing for decades. An AI agent should only have access to the absolute minimum amount of data required to perform its task. You wouldn't give a junior analyst the keys to the entire company's financial records to write a single departmental report, so why would you point an agent at an entire production database? It's about surgically defining the data scope.
And this goes beyond just limiting access. We need to be proactive about what's in the data itself. This means rigorously classifying data and, wherever possible, stripping it of personally identifiable information, or PII, before it ever reaches the model. This can be done through dedicated middleware that acts as a PII scrubbing service, anonymizing or encrypting sensitive fields at the source.
Think of it like a meticulous editor redacting a sensitive document before it's cleared for public viewing. You identify names, addresses, social security numbers, and you either black them out or replace them with pseudonymous tokens. This ensures that even if there's a data leak somewhere down the line, the most sensitive user information remains protected. Of course, all data, whether it's being fed into the agent or sitting in a database waiting to be accessed, must be secured with industry-standard encryption, both in transit and at rest.
This principle of least privilege extends directly to how the agent interacts with other systems. We have to treat each agent not as a user, but as a distinct service identity. This is where robust access control models become non-negotiable. Role-based access control, or RBAC, is a great starting point. You define roles, like document summarizer or database querier, and assign specific, granular permissions to those roles. The agent is then assigned a role, inheriting only the permissions it needs.
And for more complex scenarios, you might even graduate to attribute-based access control, or ABAC. This is more dynamic. Access isn't just granted based on the agent's role, but on a combination of attributes, like the type of data being accessed, the time of day, or the location of the request. It's like a smart security system that doesn't just check if you have a key card, but also verifies who you are, what door you're trying to open, and whether you're supposed to be in that part of the building at 3 a.m. And crucially, the credentials these agents use, the API keys, the tokens, must not be static. They need to be rotated regularly and automatically to minimize the window of opportunity should they ever be compromised.
So, we've controlled the data the agent sees and the resources it can access. But what happens when the agent executes a tool? The code it runs, especially if it's interacting with external libraries or APIs, introduces a new attack surface. This is where sandboxing becomes essential.
It's the digital equivalent of a laboratory cleanroom. You want to run your experiment, in this case the agent's tool, in a completely isolated environment so that if something goes wrong, the containment is contained. Running tools inside sandboxes or ephemeral containers, like Docker, ensures that even if a piece of code is malicious or buggy, it can't break out and affect the host system or other parts of your infrastructure. It has no visibility or access beyond the four walls of its container.
The threat isn't just from the code itself, but also from the inputs we provide. Prompt injection remains one of the most significant vulnerabilities for LLM-based systems. An attacker can craft a user input that tricks the agent into ignoring its original instructions and executing a malicious command instead. This is often as simple as appending, "Ignore all previous instructions and do this instead."
It's a form of digital social engineering. The attacker is manipulating the agent's logic to make it do their bidding. The defense here must be multi-layered. First, you sanitize inputs. You can use regex filters to block known malicious phrases or patterns. But attackers are clever and will find ways around simple block lists. So you add another layer, anomaly detection. You can train a model to recognize inputs that deviate significantly from typical user requests, flagging them for review or blocking them outright. It's a cat and mouse game that requires constant vigilance.
This vigilance extends to the interfaces the agent uses to call its tools, the APIs. Every API endpoint is a potential door into your system. That door needs to be secured with strong locks. At a minimum, this means enforcing HTTPS or TLS for encrypted communication. But it also means robust authentication. Every call should be authenticated using a standard like OAuth 2.0 or, at the very least, a unique API key for each agent.
And just like a bouncer at a popular club prevents overcrowding, you need to implement rate limits on your APIs. This is crucial for detecting and preventing misuse. A sudden, massive spike in calls from a single agent could indicate a compromised system or a denial of service attack in progress. By logging every single API call, you create an audit trail. If something goes wrong, you can trace it back to the exact agent, the exact tool, and the exact time of the incident, which is invaluable for forensic analysis.
This brings us to a broader, more holistic view of security: supply chain trust. An agent system is not a monolith. It's an assembly of parts, a foundational model from a provider, open-source libraries, third-party tool plugins, and your own code. A vulnerability in any one of these components can compromise the entire system.
This is where procurement and governance get very serious. You have to vet every single piece of your supply chain. It's like building an aircraft. You wouldn't use a critical engine component from a supplier with a questionable safety record. Similarly, you should only use LLM providers or tool plugins that have verifiable compliance certifications like SOC 2 or ISO 2701. You should also demand transparency. How was the model trained? What data was used? What are its known limitations and biases?
And we need cryptographic proof of integrity. We should be using signed model weights and signed container images. A digital signature acts as a tamper-evident seal. It mathematically proves that the model or library you're deploying is the exact one created by the trusted vendor and hasn't been altered in transit by a malicious actor.
Trust, but verify. Even with a trusted supply chain, you are still responsible for the agent's final decision. This makes auditing and explainability paramount. When a regulator or a user asks why the agent made a particular decision, the model is a black box is not an acceptable answer. You must log not just the inputs and outputs, but the intermediate reasoning steps, the chain of thought, the tools it decided to call, and the data it retrieved.
This is where explainable AI or XAI techniques come into play. These methods help us peer inside the black box to understand the why behind a decision. It might involve highlighting which parts of the input text most influence the output, or tracing the decision back to specific data sources. Maintaining this provenance, knowing which model version, which tool version, and which specific data sources were used for every single decision is critical for compliance and for debugging when things go wrong.
And things will inevitably go wrong. No system is perfectly secure. That's why the final piece of the governance puzzle is having a robust incident response plan. You need to have a playbook for AI-specific threats. What is your immediate response when a novel prompt injection attack is detected in the wild? What's the protocol for revoking and reissuing leaked API keys for all your agents?
These are not scenarios you want to be figuring out in the middle of a crisis. Your security and engineering teams need to be trained on these specific scenarios through tabletop exercises and drills. And after any incident, no matter how small, conducting a blameless post-mortem is essential. You analyze what happened, what worked, what didn't, and you feed those learnings back into strengthening your defenses. It's a continuous loop of preparation, response, and improvement.
So the key takeaway is that safety and governance aren't afterthoughts. They are design principles. It begins with a foundation of data minimization and strict access control. It's reinforced by containing actions within secure sandboxes and validating every input. And it's maintained through a trusted supply chain, rigorous auditing, and a constant readiness to respond to incidents.
It's a comprehensive framework that turns a potentially volatile technology into a reliable and trustworthy tool. We've taken our agent from being merely effective to being demonstrably safe and compliant. Now that we have this well-behaved, secure, and thoroughly evaluated agent, the final step is to release it into the world. That means tackling the formidable engineering challenges of deployment, scaling, and productionizing.
That's right. How do we ensure our agent can handle millions of users without breaking a sweat? How do we manage costs, guarantee uptime, and roll out updates without disrupting service? These are the questions we'll be answering in our next episode as we dive deep into the infrastructure and strategies for taking AI agents into production.
Welcome to AI Agents and the Model Context Protocol, where we bridge the gap between abstract theory and applied practice. In our last discussion, we navigated the critical landscape of safety, governance, and compliance. We established the guardrails, the access controls, the sandboxes, the audit trails that ensure our agents act as responsible, trustworthy entities. But a secure agent sitting on a developer's laptop is only half the story. The real question is, how do we take that secure, well-governed agent and unleash its potential in the real world?
Exactly. It's one thing to design a high-performance vehicle with the best safety features imaginable. It's another thing entirely to build the national highway system it needs to run on, complete with traffic management, fueling stations, and maintenance crews. Today, we're talking about that highway system. We're moving from the what and why of agent safety to the how of agent deployment at scale. We'll be covering the essential infrastructure, strategies for scaling and managing latency, the art of caching and cost optimization, and finally, how to ensure reliability and roll out upgrades without causing chaos. This is about transforming a brilliant prototype into a production-grade service that can be relied upon by thousands or even millions of users.
That's a perfect way to frame it. The journey from a working proof of concept to a production service is often underestimated. Let's start with the absolute foundation, the infrastructure. Once our agent's code is ready, where does it physically or virtually live?
It lives in a standardized home that we built for it. The dominant practice is containerization. Using technologies like Docker, we package the agent, its dependencies, its models, everything it needs to run, into a single, self-contained unit called a container. Think of it like a standardized shipping container. It doesn't matter if you're moving furniture, electronics, or food, the container has the same dimensions and can be handled by any port in the world. This portability is key. You can run that same container on a developer's laptop, a test server, or a massive cloud cluster without changing a thing.
And to manage all these shipping containers at scale, we need a port authority. Is that where orchestration platforms like Kubernetes come in?
Precisely. Kubernetes is the port authority. It handles scheduling, which container runs on which server, how they talk to each other, and what to do if one of them fails. You can simply tell it, I need 5 instances of my agent running at all times, and Kubernetes ensures that happens. This gives you the choice between using a managed service from a cloud provider like AWS SageMaker or Azure Machine Learning, which handle a lot of the underlying complexity for you, or running your own custom Kubernetes cluster for maximum control and customization. The managed platforms are like using a full-service shipping company, while a custom cluster is like owning your own fleet of trucks.
So we have our agent neatly packaged and a system to manage it. But what happens when our service becomes popular and suddenly we have 1,000 concurrent users instead of 10? How does our port authority handle that surge in traffic?
That's the challenge of scaling, and it's where orchestration really shines. The most common approach is horizontal autoscaling. Using tools like the Kubernetes Horizontal Pod Autoscaler, or HPA, we can set rules based on metrics like CPU utilization. If the average CPU load across our agent instances goes above, say, 70%, the autoscaler automatically provisions new container instances to distribute the load. It's like a supermarket automatically opening more checkout lanes when the lines get too long. When the rush is over, it closes those lanes to save resources.
So it dynamically adjusts the number of workers. Can we also make each individual worker more powerful?
Yes, that's the other side of the coin. For particularly demanding tasks, especially with large models, you might scale up by running your containers on machines with more powerful hardware, multi-GPU or multi-CPU instances. This is like replacing your standard checkout counters with high-speed self-scanning superlanes. A combination of both, scaling out with more instances and scaling up with more powerful instances, is often the most effective strategy.
This sounds incredibly responsive. But there's a famous problem in cloud computing, especially with these large, resource-intensive applications, the cold start. What happens when there are no active instances and a new request comes in? The user is just left waiting.
The dreaded cold start. It's the enemy of a good user experience and a critical barrier to meeting strict latency service level agreements, or SLAs. A cold start occurs because when a new instance is needed, the system has to pull the Docker image, which can be gigabytes in size, provision the resources, and then load the multi-gigabyte model weights into memory. This entire process can take minutes. For a user, anything more than a few seconds feels broken.
So how do we defeat it?
We don't let our instances get cold. The solution is to maintain a warm pool of pre-initialized instances. This is like having a fleet of taxis waiting at the airport, engines running, ready to pick up a passenger the moment they walk out the door. We keep a minimum number of agent containers running and ready to serve traffic instantly. To make this even more efficient, we use techniques like pre-caching the Docker images directly on the cluster nodes using what's called a daemon fet, and pre-fetching the model weights so they are already available locally. This combination drastically cuts down the time it takes to launch a new instance when the autoscaler needs one.
That sounds powerful in theory. Are there real-world examples of its impact?
Absolutely. There's a well-documented case from Scale AI. They were dealing with cold start times of over 6 minutes for some of their complex model serving pipelines. By implementing aggressive image caching and other pre-warming strategies, they were able to reduce that time to under 40 seconds. That is a transformative improvement that makes the difference between a usable product and an unusable one.
Keeping a pool of instances warm seems like it would solve the initial response time. But what about the work the agent has to do? Many user queries might be similar or require the same intermediate steps. It feels wasteful to recompute everything from scratch each time.
It is incredibly wasteful, both in terms of time and money. This is where a multi-layered caching strategy becomes essential. If the warm pool is our taxi with the engine running, caching is the driver already knowing the fastest route to the most popular destinations. We can implement several types of caches. An embedding cache, for instance, stores the numerical representations of frequently seen text, so we don't have to run the embedding model over and over.
And I assume we can cache the final output as well.
Of course, an LLM result cache is one of the biggest wins. If two users ask the exact same question, the second user can be served a cached response instantly without ever hitting the expensive language model. This principle extends to chat histories and session states. By caching these, we can quickly reconstruct the context for a returning user, making the conversation feel seamless and responsive while saving an enormous amount of computation. It's about intelligently reusing work that's already been done.
Reusing work definitely sounds like it would reduce latency, but it also directly ties into another major production concern: cost. These large models are not cheap to run.
Not at all, and cost optimization is a continuous balancing act. The first step is visibility. You can't optimize what you can't measure. So rigorous monitoring of token usage, GPU hours, and API call costs through telemetry data is non-negotiable. Once you have that data, you can make informed trade-offs. Does this workflow really need our most powerful, most expensive model, or would a smaller, faster model suffice? For less critical internal tasks, maybe a model running at a lower precision is perfectly acceptable and dramatically cheaper.
It's about matching the tool to the job's budget.
Precisely. You don't use a sledgehammer to hang a picture frame. This is also where the rapidly evolving model landscape comes into play. For example, a provider might release a new model like Claude 4.5 Sonnet, which offers significant performance improvements over its predecessor, but crucially maintains the same pricing structure. Making a strategic switch to a model like that can give you a free upgrade in capability and speed, directly improving your cost per task without increasing your budget.
So we've made our service fast, scalable, and cost-effective. But none of that matters if it's not reliable. How do we translate our goals for uptime and performance into concrete engineering practices?
We start by defining them. We establish clear SLAs, like guaranteeing 99.9% uptime or ensuring that 95% of all responses are delivered in under 200 milliseconds. These aren't just aspirational goals. They are promises to our users that dictate our engineering choices. To meet these promises, we build in resilience. For transient network issues or temporary model API failures, we implement automatic retries with exponential backoff.
What about more serious failures? If a model provider's API goes down entirely, we don't want our agent to keep retrying forever and overwhelm the system when it comes back online.
That's where a pattern called a circuit breaker comes in. Just like in your home's electrical panel, if the agent detects a high rate of failures from a downstream service, the circuit breaker trips. It stops sending requests for a period of time, preventing a cascade of failures and giving the struggling service time to recover. And most importantly, we need a graceful fallback plan. If our agent can't generate a response, it shouldn't just crash. It should return a default answer or, better yet, trigger a handoff to a human operator. Reliability isn't about preventing 100% of failures, it's about gracefully handling the failures that will inevitably occur.
This brings us to the final, and perhaps most nerve-wracking part of the lifecycle: updates. AI models and tools are evolving at an incredible pace. How do we roll out a new model version or an updated tool schema without breaking our finely tuned, reliable service?
Very, very carefully. The golden rule is to never do a big bang deployment where you replace everything at once. We must roll out changes incrementally. A fantastic strategy for this is a blue-green deployment. You have two identical production environments, blue and green. The live traffic is on blue. You deploy the new version of your agent to green, run all your tests, and once you're confident, you switch the router to send all new traffic to the green environment. If something goes wrong, you can switch back to blue in an instant.
And what if we want to test the new version with real users before committing to it fully?
That's a perfect use case for a canary deployment. The name comes from the canary in a coal mine. You send a small test group in first. You can route, say, 1% of your user traffic to the new version, while the other 99% remains on the stable version. You then meticulously monitor the canary group for error rates, latency, and business metrics. This is often paired with A/B testing to get objective data on whether the new model is actually performing better. If the canary is healthy and the data looks good, you gradually increase the traffic to the new version until it's handling 100%.
And throughout this process, we have to be mindful of the tools the agent is calling.
Absolutely. Maintaining backward compatibility in your tool schemas is paramount. If you change a tool's function signature, you can't just roll it out. You'll break the agent. This is why using versioned endpoints for your tools, like v1.getWeather and v2.getWeather, is a best practice. It allows you to introduce new functionality without disrupting the clients and agents that rely on the older version.
It's clear that taking an AI agent to production is a deep and multifaceted engineering discipline. It's about so much more than just the model itself. It's about building a robust ecosystem around it through containerization, intelligent scaling, proactive latency management, multi-layered caching, rigorous cost control, and safe, incremental upgrade strategies.
It is. Once you have this solid, production-grade foundation in place, you can confidently build and iterate. But as we start deploying multiple agents, perhaps from different teams or using models from different providers, we run into a new, higher-level challenge. All these robustly deployed agents need to communicate effectively, not just with their own tools, but potentially with each other. We solve the infrastructure problem only to face an interoperability problem.
That is the perfect bridge to our next and final episode in this series. Now that we've built the secure highways and deployed our high-performance vehicles, we need to ensure everyone is driving on the same side of the road and understands the traffic signals. Next time, we will tackle the critical topics of interoperability and standards. We'll explore why a common protocol for function calling is so essential, and how emerging standards, including the Model Context Protocol, are aiming to solve the AI ecosystem's Tower of Babel problem, paving the way for a future of truly collaborative and composable AI systems. Welcome to the final episode of our journey together on AI agents and the Model Context Protocol. Over the past 8 episodes, we've dissected everything from the core of an agent to the complexities of deploying it into the wild. We've built it, we've given it memory, we've evaluated it, and last time, we navigated the challenges of productionizing it at scale.
But once an agent is deployed, a new critical question emerges. It's running, it's stable, but is it an island? In a world where technology thrives on connection, how do we prevent our sophisticated AI agents from becoming isolated, brittle systems, unable to speak to or understand anything outside their own narrow, custom-built world?
Precisely. That question is the heart of our discussion today. We're not just talking about making one agent work. We're talking about building the foundations for an entire ecosystem of agents to collaborate. This is the challenge of interoperability. So how do we build this future? Today, we'll explore the crucial standards and protocols that make it possible. We'll examine the current fragmentation and function calling standards, how we can leverage existing web standards like OpenAPI, the power of centralized tool registries, the necessity of standardizing our prompt and observability layers, and finally, the emerging community protocols that are paving the way forward.
We've laid the groundwork for building robust individual agents. Now we're zooming out to see how these agents can become part of a larger, interconnected whole. This isn't just about convenience. It's about unlocking the next level of capability, where agents from different developers, powered by different models, can work together seamlessly.
Let's start with the most fundamental point of interaction, how an agent calls a tool. Right now, if you're building an agent, you face an immediate challenge. The major model providers, OpenAI with its latest models like O3 and GPT-4o, Anthropic with Claude 3.5 Sonnet, and Google's models all support function calling. They all use a similar concept, a JSON schema to describe the function. But the devil is in the details.
It's like traveling in the early 20th century. You arrive in a new country, and not only is the language different, but the plug for your electric razor won't fit the wall socket. Every single LLM API has its own protocol details, its own unique socket. For a developer, this means you can't just write one piece of code for tool interaction. You're forced to write specific code paths for OpenAI, another for Anthropic, and yet another for Google. It's a classic fragmentation problem.
This isn't just a minor inconvenience. It's a significant barrier to creating truly model-agnostic agent architectures. Every new model you want to support adds another layer of complexity and maintenance overhead. This is precisely the problem that a unifying standard like the Model Context Protocol, or MCP, is designed to solve. It acts as a universal adapter, providing a single, consistent format for these interactions, allowing you to switch the underlying model without having to rewrite your entire tool calling logic.
It standardizes the plug, so to speak, so your agent can get power from any outlet. But what about the tools themselves? How do we describe them in a way that's both human-readable and machine-understandable, and that aligns with decades of software engineering best practices?
That's where we can lean on existing battle-tested standards, specifically OpenAPI and JSON schema. For anyone who has worked with web services, OpenAPI, formerly known as Swagger, is the lingua franca for describing RESTful APIs. We should start treating every tool our agent uses as a self-contained, schema-based RESTful API.
Let's make that tangible. Imagine your agent needs to check a flight status. The Check Flight Status tool isn't just some abstract function in your code. Think of it as a microservice with a clear contract. It has an endpoint, it accepts specific parameters like airline and flight number, and it returns data in a predictable format. The OpenAPI specification allows you to define that contract with perfect precision.
And the beauty is, from that single open API specification, you can automatically generate the exact JSON function schema that the LLM needs to understand how to call it. This approach brings immense discipline to agent development. It forces you to think clearly about your tool's interface, it makes your tools self-documenting, and most importantly, it aligns with emerging standards for how LLMs will interact with external plugins and services. You're no longer just hacking together functions, you're building a robust, well-defined API layer for your agent.
This also creates a wonderful separation of concerns. The team building the flight status tool can focus on making it reliable and efficient, defining its capabilities clearly in the open API spec. The team building the agent doesn't need to know the inner workings of the tool, they just need to consume that spec. This modularity is key to building complex systems that can actually scale. But then a new problem arises. If you have hundreds of these well-defined tools, how does your agent find the right one for the job?
That leads us directly to the concept of tool and function registries. Hard-coding a list of tools into an agent is brittle. What happens when a new tool is developed or an existing one is updated? You'd have to redeploy the entire agent. A far more elegant solution is to have the agent discover and load its tools dynamically.
This is like moving from a world where every application comes with a fixed set of features to the world of app stores. An app store is essentially a central registry. Your phone doesn't know about every possible application in the world. It knows how to connect to the App Store, search for a capability it needs, say photo editing, and then download and install the right app. A tool registry does the same thing for an AI agent.
Exactly. A service like the MCP registry provides a central catalog where you can publish the definitions of your tools. Your agent, at runtime, can then query this registry to find tools relevant to its current task. This makes agents incredibly flexible. A customer service agent could dynamically load a new process refund tool that was just published by the engineering team without any downtime or code changes to the agent itself. It decouples the agent's core logic from its capabilities.
So we've established how agents can find and use tools in a standardized way. But as we discussed in our episode on observability, if you can't see what the agent is doing, you can't manage it. And just like with tool calls, the logs and traces produced by different agent frameworks can be wildly inconsistent.
This is where standardization needs to extend to the operational side of things, into the realm of LLM ops. We need to adopt strict conventions for logging prompts, the model's responses, and every subsequent tool call and result. This isn't just about debugging, it's about governance, cost tracking, and performance analysis.
And a new generation of platforms is emerging to help with this. Tools like Langsmith, Langfuse, or Langwatch are designed specifically for the observability challenges of LLM-based systems. They provide a structured way to capture the entire lifecycle of a request, from the initial prompt to the final answer, including all the intermediate reasoning steps and tool interactions. Think of it as a flight data recorder for your agent.
And within that, prompt management becomes critical. We need to treat our prompts like code. That means tagging them, versioning them, and tracking their performance over time. When you find a prompt that works exceptionally well for a specific task, you need to be able to save it, test it, and deploy it just like any other software asset. Integrating this process with LLM ops platforms allows you to run A/B tests on prompts and scientifically measure which changes lead to better outcomes.
All of these pieces, standardized function calls, open API schemas, tool registries, and structured logging, are converging into a set of community standards. This isn't about one company dictating the rules, it's about the ecosystem organically developing best practices. Following an emerging protocol like the MCP spec is a bet on cross-vendor compatibility. Adhering to the safety guidelines published by OpenAI and Anthropic for function use is essential for building responsible agents. If you're building consumer-facing features, complying with UI plugin standards is non-negotiable.
And it's important to recognize that the ecosystem itself is constantly evolving. A year ago, most examples were dominated by a single model provider. Today, the landscape is far more diverse and vibrant. We see OpenAI's latest models like O3 and O4 Mini pushing the boundaries of reasoning and function calling capabilities. At the same time, Anthropic's Claude 3.5 Sonnet has shown itself to be a leader in tasks requiring complex computer use and coding. The smart developer is building systems that can leverage the best model for the job.
The tooling is evolving just as quickly. LangChain continues to be a fantastic representative framework for tying these components together. But for more complex, cyclical agent behaviors, developers are now turning to graph-based orchestration tools like LangGraph, which allow for much more sophisticated control flow. And for systems that require multiple agents to collaborate, frameworks like Crew AI are providing powerful abstractions for multi-agent coordination. The theme is specialization and composition.
It's a fitting place to end our series. We've journeyed from the atomic unit of an AI agent, its core reasoning loop, all the way up to this macro view of a collaborative, interoperable ecosystem. We started with a single agent, gave it tools, gave it memory, learned how to evaluate it, secured it, and deployed it. And now we've connected it to a universe of other agents and tools through the power of standards.
The ultimate takeaway from our entire discussion is this: the future of artificial intelligence isn't a single monolithic superintelligence. It's a decentralized, dynamic, and collaborative network of specialized agents. Interoperability and standards are not just technical details. They are the social contract of that network. They are the shared language that will allow us to move from building clever individual tools to composing truly breathtakingly intelligent systems.
It has been an incredible 9-episode journey, and we want to thank all of you for listening and joining us as we've explored the foundations and the future of AI agents and the Model Context Protocol. The principles we've discussed are the building blocks for the next generation of software, and we are all architects of what comes next.